All electronic components have losses when current passes through them. In transistors, this comes in two main forms: conduction loss and switching loss. Conduction loss is just the result of the resistance and voltage drop of the device. It's a function of the current passing through the device and, to be honest, isn't very interesting. Switching loss, on the other hand, occurs during the transitions between on and off, when the transistor is somewhere in the middle, acting like a big resistor. So can we just switch really fast and make those transitions as short as possible to get rid of switching losses? No. That's because switching losses are made up of 4 distinct parts, each of which can be attributed to a different parasitic component of a transistor. The first and most intuitive form of switching loss is the one we've already considered, which we're going to call overlap loss because the voltage and current waveforms overlap while the transistor is switching, just like we can see here on the scope. It can be approximated by multiplying the voltage by the current to get the power, and then by the time it takes to switch to get the energy. This then needs to be halved either once or twice depending on how you want to approximate the switching waveforms. The next type of switching loss we'll look at is capacitive loss. All energy stored in the capacitance of the switching node, the part of the circuit being switched, has to be dissipated by the switch when it turns on, in the form of a brief current spike like this. Essentially, the transistor is shorting a charged capacitor every time it turns on. Usually most of this capacitance is internal, so the current spike can't be measured, but in this case I added some more so that it can. This loss can be approximated by using the standard capacitor energy equation of half CV squared, though this assumes that the capacitance is constant, while in reality transistor output capacitance varies quite a lot with voltage. This equation also shows us that capacitive loss is only influenced by capacitance and voltage, not current, which means we even get it with nothing connected to our switches, as they just continuously charge and discharge the switching node. Whenever capacitance is at play, one often doesn't have to look far to find inductance trying to join the fun, and switching loss is no exception, as we also have loss resulting from the energy stored in the commutation loop inductance. Once again, all energy stored must be dissipated, though because inductors are the opposite of capacitors, everything flips around. So instead of a current spike at turn on, we get a voltage spike at turn off. The equation for this energy is also very similar to that of the capacitor, half Li squared. Unlike the capacitance, the inductance doesn't really change at all, so this equation is probably the most accurate of the lot. The final form of switching loss is caused by diodes and their naughty behaviour, known as reverse recovery, a short period when a diode continues to conduct but in the wrong direction, before it realises what it's doing and turns off. Oops. This only happens in bipolar diodes, not Schottkys, but as MOSFETs contain inherent bipolar diodes, it affects the majority of modern circuits. Reverse recovery manifests as a brief current spike, effectively shoot-through where both switches are conducting and the current rises extremely quickly until the diode's reverse recovery is complete and it turns off. This causes quite a few issues, particularly for EMI, but today we're focusing on the additional switching losses it creates, which are by far the hardest to predict, as reverse recovery behaviour is affected by the loop inductance, DC voltage, temperature, switching speed, and much more. If you really feel an urge to calculate something, a common but not very accurate approximation is to multiply the quoted reverse recovery charge by the DC voltage. So, in summary, high resistance during switching transitions results in overlap loss at both turn on and turn off. Capacitance causes loss when its stored energy is dissipated during turn on. Likewise, inductance causes loss when its stored energy is dissipated during turn off. Finally, bipolar diodes cause reverse recovery loss during turn on of the opposite switch. Device datasheets normally combine these into 3 quantities: E on, E off, and ERR, each representing the amount of energy dissipated when switching at a certain operating point. E on is made up of the capacitive loss and some overlap loss. E off represents inductive loss and some more overlap loss. And ERR is simply the reverse recovery loss. For all the demonstrations in this video, I've made this synchronous buck converter and an accompanying plug-in board, which allows us to easily view the voltage and current waveforms on an oscilloscope. If you'd like to see this or something similar as a product, let me know in the comments. The losses from the energy stored in the capacitance and inductance are easy to overlook, as they're often small relative to overlap losses. But while overlap loss can be lowered by switching faster, reducing the time between on and off, the stored energies are constant, irrespective of switching speed, so the same amount will always be dissipated. It's like eating a chocolate bar. No matter how fast you eat it, it's still got the same calories. And just like how eating quickly can make you feel a bit sick, turning on too fast can actually make reverse recovery worse, because the current is able to rise faster and further before the diode starts blocking. Clearly, we need a different approach to reduce these losses. If we can make the voltage or current zero when the transistor switches, then in theory we can completely eliminate at least some of the sources of switching loss. This is called soft switching, and as you can make voltage or current zero for turn on or turn off, there are 4 different ways it can be done. Zero current turn on is easy to achieve in certain circuits. If there's an inductor in series with the switch that has no current before turn on, when the switch does turn on, the current will increase very slowly relative to the switching, as its rate of change, the dI/dt, will be limited by the inductance. So the whole turn-on transition will happen before the current has had the chance to increase and produce some overlap loss. Most converters operating in discontinuous current mode or DCM will achieve this type of soft switching, with the most common example being a DCM flyback converter, like those used in the majority of small switch mode power supplies. In a similar light, zero voltage turn off can also be very easy to achieve in circuits with large switch node capacitance, which prevents the voltage across the switch rising too fast, limiting the dV/dt. This sometimes takes the form of discrete capacitors added in parallel with the transistors, but a lot of the time the parasitic output capacitance is enough. Examples of converters that use capacitors to ensure zero voltage switching at turn-off are the dual active bridge and the phase-shifted full bridge, which are very similar topologies that crucially both employ zero voltage turn-on, eliminating the losses caused by that additional capacitance. Unfortunately, neither of these soft switching strategies help with stored energy losses or reverse recovery, and only reduce overlap loss. To eliminate these, we need a way to recycle that stored energy back into the converter, rather than dissipating it into the transistors, and for that we use zero voltage turn-on and zero current turn-off. We'll start with zero voltage turn-on because that's much simpler to implement, all thanks to diodes. Turns out they are good for something. This is because an anti-parallel diode, like a MOSFET's body diode, clamps the voltage when current flows in reverse. So if that's happening before we turn on, the voltage across the transistor is already basically zero, and both overlap and capacitive energy losses are eliminated. This occurs in all synchronous rectifiers, MOSFETs used in place of diodes, like the low-side MOSFET of this synchronous buck converter, which will always experience zero voltage turn-on. We can even see it happening because the diode forward voltage isn't quite zero, so the voltage across the switch goes a little bit negative before it turns on and brings that voltage to zero. Interestingly, if we swap the output inductor for one with lower inductance, increasing our current ripple to the point that it actually goes negative, then we end up getting the same zero voltage turn-on for the top switch as well. We can see this because the switch node voltage is now clamped high rather than low before that switch turns on. Need help finding the best inductor for your next project? Check out Coilcraft's DC to DC optimizer tool, which will help you find the perfect inductor from their extensive product range. Simply select the topology you're using and enter your converter specifications to be treated to a big list of potential inductors, which can be narrowed down further using additional filters. You can then select a few inductors from the list and get some very useful graphs, including the current waveform you can expect, a breakdown of the losses that will occur in the inductors, and their saturation curves. Everything you could ever need to find your inductive soulmate. So when you're next hunting for the perfect inductor, check out Coilcraft's DC to DC optimizer tool using the link in the video description. The reason that using diodes for zero voltage turn-on works is because during the dead time, the period where both switches are off, the energy stored in the output inductor forces current to continue flowing, which charges or discharges that pesky switch node capacitance, eliminating the need for the transistor to dissipate that stored energy, and instead recycling it within the converter. The speed that capacitance is charged or discharged is dependent on the inductor current. In the case of this buck converter, if the load increases, shifting the current ripple up and reducing the negative portion, the voltage swing slows down. If the current is too low, the voltage won't reach zero before the switch turns on and it'll hard switch, so the dead time needs to be long enough for this to happen. However, if the dead time is too long, current will spend ages flowing through the inefficient diode before the transistor turns on, introducing additional conduction losses that could outweigh the saved switching losses. Some topologies, like the phase-shifted full bridge we looked at in the last video, add an inductor purely for the purpose of charging and discharging the switch node capacitance to achieve zero voltage turn-on. As this inductor current is dependent on the load, many topologies like the PSFB are unable to soft switch at light load, contributing to reduced efficiency. Zero voltage switching has more of an impact in higher voltage converters, because the diode forward voltage that's still being switched represents a much lower proportion of the full DC voltage that would otherwise be switched. Now, there's an unfortunate problem that arises with fancy gallium nitride devices, as they don't really have body diodes. I say don't really because they do have third quadrant conduction, meaning current can flow from source to drain when they're off, like in a MOSFET. But the voltage drop is large and not constant, so can't be relied on to clamp the voltage like a diode. In some respects, this is a good thing, because without any body diode, GaN transistors have no reverse recovery to worry about, which is one of GaN's key advantages over silicon. But this does mean they don't make great synchronous rectifiers. This is the reason GaN is rarely used for synchronous rectification in isolated topologies, as we saw in both the small GaN power supply and the big SiC one, where silicon MOSFETs were used for this purpose in both. When GaN devices are used for synchronous rectification, like in buck converters, discrete anti-parallel diodes are usually added to do the voltage clamping. Here's the high-frequency current source I designed for the video on PCB trace inductance, which is just a half-bridge and inductor like the synchronous buck converter. You can see the diodes I added to clamp the reverse voltage next to the GaN devices, and if we probe the switching node, we can see them clamping the voltage just like on the other board, but at 50 times the switching frequency. One problem with adding diodes like this is that they add additional capacitance to the switching node, though this can be accounted for in the design with more inductance and a longer dead time. A different approach to zero voltage switching is to synchronize the turning on of the switch to when the voltage naturally reaches zero. Of course, this only happens in certain situations, but one example is a type of solid-state relay called a zero-cross SSR, which turns on when the AC mains voltage reaches zero, preventing a sudden rush of current as capacitors get charged up. This concept of precisely timing the turn-on for the voltage minimum is also done in most modern flyback converters found in small power supplies, and it's called quasi-resonant operation. These rely on the oscillations formed by the switch node capacitance and the transformer inductance after all energy has left the secondary side of the transformer. This turn-on isn't at 0 volts, but is at a much lower voltage than the DC, so while it doesn't eliminate the turn-on losses, it does reduce them quite a bit. Zero current turn-off is by far the hardest type of soft switching to implement, as there's no equivalent of a body diode we can rely on like for ZVS. The most common example is in a resonant LLC converter, where switches turn off at the perfect time, just before the current starts increasing again, like the strategy for zero voltage switching we just looked at. This works best when the converter is operating at its resonant frequency, as otherwise some current will still be flowing when the switch turns off. This is why fixed ratio LLC converters are used for the highest efficiency and power density converters on the market, as setting the output voltage proportional to the input voltage, as opposed to making it a fixed value, allows the converter to always operate at that sweet resonant frequency, meaning all switching losses can be eliminated. This mode of operation isn't very useful for applications like battery charging, which require a wide range of output voltages, but for something like a switch mode power supply, it isn't much of a problem, as the input voltage is already regulated by the power factor correction circuit. Zero current turn-off is also possible in many other topologies, with the addition of extra switches and resonant components that act to steer the current away from the main switches while they turn off, for example in an auxiliary resonant commutated pole inverter. A secondary benefit of soft switching that's often as big of a deal as the improved efficiency is the reduced electromagnetic interference, or EMI, as this is primarily caused by fast-changing voltage and current when the switches do their thing. Soft switching slows down these transitions and therefore reduces the resulting electromagnetic noise. So, in summary, all 4 variations of soft switching reduce or eliminate overlap loss, but only zero voltage turn-on and zero current turn-off are able to help with stored energy losses and reverse recovery. Zero voltage turn-on occurs naturally in any switches used for synchronous rectification and can be made to happen in all devices in topologies that have an alternating output current. Zero current turn-off is tricky as it requires a topology where current will naturally reach zero, which is pretty much just resonant converters like LLC. If you want to know how to measure switching loss in hard-switched applications like inverters, I made a video on double pulse testing last year, which could be worth a watch. Anyway, that's it for this video. I hope it was useful and thank you very much for watching. Bye!